So for our next talk, we have Zipline plus Julia parting ways with our Julia simulation after 100 million miles. Let's welcome our speaker.
Mhm. So yeah, despite the Zipline plus Julia here, unfortunately, this is going to be a Zipline minus Julia talk. Uh, we have been using Julia for about 7 years, and we are no longer using Julia. So this is kind of a bummer of a talk, especially for me, because I am an active member of the Julia community, and I still enjoy Julia, but professionally, I have moved on a bit. But first, I want to give a big thank you to Julia Hub, because when they first reached out about kind of giving an update on what we've been doing for the last few years since the last time we gave a Julia talk, JuliaCon talk, we hadn't decided to move away from Julia, and I, accepted, and that was going to be great. And then we got the news that we will not be using Julia anymore, and I reached out to them. They were like, you know what? That's really useful information for our community to have, and it's useful for us to grow. So go ahead and give the talk. So kudos to Julia Hub. I thought that was a cool move. And I appreciate it just as a Julia user and community member, that's kind of the, attitude there. But yeah, so who am I? I am Jonnie Diegelman. I'm a controls and dynamics engineer at Zipline. We are a autonomous logistics company, mostly with flying things, but if ever in the future we wanted to have driving things, that could happen too. But yeah, our main focus is delivering things autonomously. On GitHub, you could find me either Jonnie Die or Jonnie Diegelman. Those are my two profile pictures you'll see also in different circles in Julia. I maintain and wrote some Julia packages, including component arrays, concrete structs, and simulation logs. I sometimes maintain them. I could do a better job. Thankfully, component arrays is now in the hands of SciML, so there are more people working on that one. And yeah, this was going to say something about being a father and have my family and everything, but as I was going through my phone, I saw this little flyer that my daughter made of my son, and I just decided to change this, and that's our dog, Mayhem, right there. So yeah, who is Zipline? I kind of briefly touched on it, but we do autonomous delivery of things. So we started in blood, medical supplies, vaccines, and stuff like that out of Cote d'Ivoire, Ghana, Japan, Kenya, Nigeria, Rwanda, and the US. We started in Rwanda. But yeah, so our first vehicle, this one's been flying since 2016, is a long range. That's like 80 kilometers out and then back, at least. I think it might be a little bit more, actually. Fixed wing, there's no landing gear or anything. We deliver via parachute. We take off with a launcher, and it's caught in the air, which you'll see in a second. Right here. It snatches out of the air. So this was all developed using Julia for a lot of engineering analysis and simulation and stuff for controls design. And it has taken us more than 100 million miles flown, which is a pretty far distance. And that has resulted, in some great things like 51% fewer deaths from postpartum hemorrhaging in the hospitals that we serve. So I think despite the fact that this is kind of like a sad moving away from Julia talk, there's also like a really nice, Julia really did help us do some things that I think had pretty good impact in the world. Here's our Platform 2 vehicle. This is the one that I've mostly worked on because I've been with the company for 3 years. And so through most of the design of this vehicle, this one's shorter range. It's vertical takeoff and landing. It is a 2-vehicle vehicle. That little guy's called the Zip. It gets lowered for much more precise delivery than we could do with the parachute thing. It has much increased payload capacity, a lot lower infrastructure than the other one. with charging stations and loading points. We are currently operating in Dallas, Fort Worth, Texas in the US, as of, a couple months ago. Um, but yeah, the whole point of this vehicle is to kind of like expand our capability of what we can do, like in healthcare, like reverse logistics, if you need to take a sample back to the lab or something like that. Or, there's the food delivery use case or retail, all sorts of things. So this really helps us like deliver directly to customers a lot easier, like people at their houses and stuff. So yeah, I'll talk about like kind of the brief history of Julia at yeah, Julia at Zipline. So back in 2019, Tucker McClure gave a talk called A New Breed of Vehicle Simulation. I'd encourage you to look it up. It's a great talk about our company using Julia. In 2021, we created what we call modeling.jl, which is like our in-house model-based design and simulation framework. So we created that mostly for our new P2 vehicle as we were starting to bring it up. And then we created what's called like Starling on top of that, which is like our software in the loop, hardware in the loop, which I'll talk about this all in a second. And then now, unfortunately, we're chopping it off. So yeah, briefly, let me go into what modeling.jl is. So it's a hierarchical modeling framework. You think kind of like Simulink, but without the graphical user interface. It's all code, but it's still like models can contain models inside of them, and data gets passed around by parent model between different child models and that kind of stuff. So in this example here, you might have a really simple world with an environment and a really simple aircraft in it. It's configurable. You could swap out that aircraft for something maybe similar. You could have like a point mass kinematic aircraft if you only want to test certain parts of the software that don't care that much about physics. Every little part of the simulation can be configured. It's causal as opposed to like acausal, like modeling toolkit. So data flows one way, the way that you have to do in programming. Yeah, it's also continuous in discrete time. So models, there's a continuous side where they talk to the ODE solver and they give their derivatives, and then there's discrete stuff like software that doesn't have any continuous and only runs in discrete time. And then there's stuff in between. Actuators and sensors are like canonically the bridge between the discrete and continuous time worlds. So yeah, it can handle a bit of both. It's functional-ish to where none of the models are allowed to update their own states. They all have to pass out a named tuple that tells how to update the state derivatives and all the children to the framework. This is really helpful for things like basically you could get into a lot of trouble with ODE solvers if you allow your models to update their own states or state derivatives, because that breaks a lot of the assumptions that ODE solvers have. So this prevents that. And it's models all the way down. Everything in it is a model. Everything we do is a model. Models can initialize with an init function. They could do continuous dynamics, which basically FC function tells the solver how to take time derivatives, and then FD for any time you need to do an instantaneous update of some variable, whether it's a discrete variable or continuous. So Starling is built on top of modeling.jl. In this picture, that little wood there, I guess, is modeling.jl, and the Starling is on top of it. I didn't really think of the metaphor very well. But so it's a software in the loop that runs either synchronously or asynchronously in real time, and also has a hardware in the loop mode. For us, what that means, hardware in the loop, is like you're actually running on your flight target, like on your like flight computer that you would be running in real life. It could also mean that you have actuators hooked up and stuff like that. There's like a whole range of what hardware in the loop could mean. But yeah, so all of the process launching and everything, orchestration, it just happens through the models in here. And what we're talking about in scale, it's like about, yeah, like over 60 external processes that it's talking to, and then like a lot of processes, like 25, that it's like mocking internally in Julia. So there's quite a few processes, and then there's, I'd say, like 300 something continuous states that we're integrating. So that's about the scale that we're doing here. So yeah, I guess the main point of the talk is like, what challenges did we face in Julia, and like, why did we ultimately make the decision to move away from Julia after using it successfully for quite a long time? Before that, like, or one of the challenges is kind of not necessarily Julia based, but like really plays into this, is there's kind of two cultures of engineering simulation that I think that we don't always think about too much, but like one is the physics focus, which I think probably a lot of the people in this room are going to be more on this side, where to you, a simulation means solving a differential equation, and anything else is like extra on top of that. Whereas the software focus, if you're, writing flight software, robotic software, and like that's your main focus, simulation really means like stepping algorithms forward in time, kind of. And then physics is just like another algorithm that you're stepping, kind of. Whereas in the physics side, flight software is just like another model in your solver. So in the physics one, the ODE solver controls time. In the software one, the orchestrator discretely steps time. Why this matters is in the physics focused one, the continuous states across different models they can sub-step together, and that really matters for how like solvers work. Like, you can't really have the same modular physics if everything just has its own step function, because if you take like the old RK4 method or something, it's doing multiple sub-steps per continuous step. And if you can only step time discretely, you have no way of actually communicating across sub-steps. So the physics focused version can handle more, but it's also a lot more clunky and kind of like difficult to use, which is why, like, when possible, like the software focused is like kind of an easier way to go. So a lot of different types of robotics applications and stuff might focus more on the software focus side, because you can actually make a much easier to plug into simulation. So one of the big problems we had with Julia specifically is basically all of our flight software and everything depends on Julia, because Julia simulations gate all of our flight software from getting through CI. Like, basically, you want to merge something that's going to get run on the vehicle, like it needs to run through hundreds of different tests and validation suites that are running full simulations to make sure that the behavior is correctly. And so Julia is this little thing, and it is maintained by a small handful of people, and then like hundreds of people are writing the other code that depends on it. So when something like breaks in CI or something like that, it's usually, there's a small handful of people, if it was in the simulation, that can actually fix it, and everyone is kind of waiting for them. So another problem we kind of hit is, type instability is always a thing, but there's a lot of things that it breaks in our specific workflow. But you kind of have this cycle where it's like, okay, you don't want it to break. So the way that you prevent things from breaking is you put in regression checks and make sure you can't write more type stable code, but you can't do that until you get your code type stable. So you spend a good amount of time trying to fix all the type instability. But, if there's one or two people in the company that are proficient enough in Julia to do that, then it takes quite a bit of time. And in that time, new type unstable code is merged, and you didn't get in the regression test to fix it, and you're back in the loop. So this was a loop that we had a really hard time breaking out of. And I would encourage anyone in here, if you're taking on like a similarly scoped problem, deal with type instability first, put in regression tests first, and then build on top of it. It's definitely not something that you want to come in and clean up later. It's a, there's no such thing as premature optimization when it comes to like type instability. Like it's always the correct way to go. Another issue we kind of had is JIT compilation. Modern build systems like to, they want to run a bunch of tests in parallel, and they just want you to like tell them what to compile first, and then it's going to distribute that across all that. But, JIT compiled languages don't play super nicely with that workflow. Yes, you can run a warm-up run and you could like cache the compilation results, but if your simulation is extremely configurable and each different configuration of the simulation is like an actual different type, which maybe that was also a mistake, but that really can cause some challenges here. So like this is where type instability and JIT compilation like kind of come up in real life. So this is a plot from like our real-time sim, like running in hardware in the loop, where if we fall behind real time too much, like the vehicle in simulation will like just fall out of the air. So this is something that we saw that we were running 2 full mission warm-up runs before we ran this real-time sim, and we would still hit what we actually saw was JIT compilation in the middle of the sim, because we had type instability and we were going down a code path that maybe the other ones possibly weren't or something. So you would still have to hit JIT compilation despite the fact that you did a lot of other warm-ups. So yes, JIT compilation like plus type instability is like especially bad things. So yeah, what are we using instead of Julia? So a brief aside, there's a thing called carcinization, where nature tends to like to evolve things into crabs. What does this have to do with software? Well, there's a software version of carcinization, which is the tendency of programmers to want to rewrite things in Rust. And if you've ever met someone that uses Rust, you probably know this type of person. But it's because they really love writing Rust. And I've, been using it for a while too. And like, I get where they're coming from, especially around the tooling. And this joke works because their mascot is a little crab named Ferris. So yeah, what this looks like for us is this kind of like Ouroboros thing, except for the snake is eating other languages' tails, which I guess is just cannibalization. So like, why do people love writing Rust? Like, on the surface, I wouldn't have expected Rust to be a language that people love. It's kind of like if you were to say writing concurrent programs is difficult. What if we wrote a language that made serial programs as difficult to write as concurrent programs? That's kind of like the pitch of Rust, and it sounds like it wouldn't work at all. But the tooling around it is so good that most people don't actually complain about it, because mostly the compile time errors that it can get are like really nice. So for example, we have this function here, and I want to just like add an extra input that it's not expecting. What does the errors look like? So we see right here, we get 2 different errors. One of them says, okay, you tried to access some foo value from inputs. That's not one of the available fields. So here's a nice little thing that tells you exactly what is available there. And then you get another error right below it that all ran at once that tells you, hey, this function expected 3 arguments, you gave it 4. It's very clean, very easy to just find exactly what went wrong. It points to what went wrong. You could even say cargo fix, and it will fix some of these things automatically for you. Like, it's really cool. And what's really neat is like when you're working on a big project, you will like go to compile something and you'll get like all of your errors just at once, and you could just go through and fix them. You don't have to do the cycle of run my code, hit an error, run my code, hit an error, fix, run in, and go back and forth. Especially when you have JIT compilation, that means, you might be hitting that error a couple minutes into your simulation or something, and that could take a long time. So it's a really long development cycle there. So this kind of like fixes that by like catching it all at once. Um, what's my time, by the way? I don't. Okay, cool. Good. I have some time to like talk about like some of the other cool stuff. And some of this stuff actually we can have right now in Julia, and I think it fixes some problems that are nice. So I talked about before this case of you have these different simulation configurations where every one of them is a completely different type because they're parameterized by different types. So like Rust enums kind of like fix this problem. And we have this in Julia. It's either sum types or Moshi. There's like a few different packages that implement these like sum types. And the idea here is that like, let's say you want like you have that situation, or like you have a bunch of different types and you want to make an array of all these different types. That would normally be bad in Julia because it would be abstractly typed, right? You can't hold a bunch of different types in an array and expect, a fast program. But with this, like everything is one type that just gets represented as one type that with like three different variants. And then you could have like a match statement that you could kind of like ergonomically go through and hit stuff. The downside here is it's basically as if you're doing like an if statement where someone else can't buy into your like they can't write a method for this if you're going this route or whatever. You can't add on a new vehicle type or something. So there are some downsides as opposed to like abstract types or whatever, super types. But like it's really nice if you're like the end user writer of the simulation and you know all of your variants and you control all those. We could have this right now, like almost the exact same syntax in Julia too. We do have this. Traits are really nice in Rust. Another reason people like it is it defines exactly what will be implemented, and this actually is what helps the compiler know whether certain types have certain methods implemented or not. So like, we might have a trait that's like number of doors, and we want to implement that for vehicles and houses. And the cool thing about this is if you're setting a function signature or something and you only want to allow like a type that implements a number of doors, like it will strictly enforce that. And yeah, it's a really nice thing. And if you've ever like worked in Julia with like interfaces like iterator interface or like broadcast interface, or if you written your own array package like I have, like there's a lot to be desired in knowing how to implement interfaces in Julia. Like I've had some struggles with it and I think other people have too. So it would be cool to have like really like nailed down this is what your interface looks like. But it's not all like one way. Julia actually has like a lot of really cool stuff that Rust doesn't that, definitely like I'm missing when I go to Rust. So like I think it's worth like at least pointing that out. SciML ecosystem obviously is great. Package composability is like another huge one. Rust has the same type parameterization, but it's more like a cultural thing. Like in Julia, like our culture is to always want to be composable, and like languages kind of other languages don't have that. Better prototyping experience. And then, like a little type instability is a treat sometimes, because if you want to set up your configuration of your vehicle from like a JSON file or something like that, like that all needs to be done at runtime. Really hard to do like in a compiled language, but if you could have a little bit of type instability in your initialization of the simulation where performance doesn't matter, you will build a concretely typed thing that can run through the loops really fast. And that's like a really cool kind of like superpower of Julia that I don't think gets talked about enough. So yeah, that's kind of the end of what I had. I hope to have a good amount of time for questions.
Okay, so we have a lot of time for questions. Let me start. I don't know who raised the hand first. So, uh,
Do you miss multiple dispatch?
Um, let's see. I think you kind of like end up using it, at least I kind of end up using it less than I thought. Or like sometimes you kind of overuse at least I tend to do it. I overuse multiple dispatch in cases where it's like I would have been fine to like not even be polymorphic and just like write a separate function for things. But I use multiple dispatch just because, it looks, whatever the way it does. I do kind of miss it just because I've been using Julia for long enough that my brain just kind of thinks in multiple dispatch ways. But like, I've also tried to like sell it on other people that like use Rust, and a lot of times they don't see like what like how it's nice until you give like an example of like adding two matrices or something like that. But like I think those use cases are also like a little bit more like rare in the type of code that we write. Mm, mm.
Thank you. This might be a two-part question, but they're related. You mentioned the dependence on just one or two people who know the GNC Julia library as an issue. Could that also be seen as a benefit where because of Julia's high-level expressiveness, one or two people was enough? And how many people do you think it will take to support a Rust implementation? And the second part, if I may, is have you tried recruiting additional Julia developers to expand that team? And how did that work out?
Yeah, no, that's a great question. It's actually one that I wanted to bring up, but I kind of forgot to hit on it. So one of the things I forgot to mention is our entire flight software stack, for the most part, is written in Rust. So we just have this like incredible like depth of like knowledge in Rust to where we can always lean on those people. Like if you're writing the simulation, we just don't have that in Julia. Yeah, and then the second point is like hiring for Julia. One of the things that like we want to make sure of when we're hiring people is that like we really want to make sure that we get people that like are really good at like, their domain knowledge and good at solving problems and thinking through stuff like that. And like kind of at the lower end of the list is whether people are good at certain software or programming languages and stuff like that. Because at least to us, like that stuff can be learned faster than, the engineering skills that take a lot longer to build up. Like most people that use Julia in our company, like we don't hire anyone for the most part that I know that except for me that like had Julia experience before the company, but like the ones that use it like got up to speed pretty quickly. They're just not able to like dive into the deep parts of, fixing, type instabilities and stuff without more experience. So, yeah.
Chris, do you have questions?
Yep. So I was wondering if you could speak a little bit more about, like what are you, for this way that the programming is being used, right? It's being used for this use case that's real time, embedded and whatnot. Like, what are you giving up when you go down this decision to Rust, right? I mean, because I think that it's pretty clear. Like, okay, you have a software engineering division, and they're the ones that got to maintain code, and they're like, oh, of course, the locking it down makes it easier to maintain. So there's a lot of pros there. I could see where that could come from, but I mean, you're the controls engineer though, right? So what are the certain things that like are you able to still do all of the controls analysis, or are you now you're kind of saying, oh yeah, now we don't do this as controls analysis or whatnot, we might have a little bit less controller efficiency, because there's a trade-off in here. Could you describe what happens with this trade-off in terms of like the how physical you get and how physical you're now able to do, and how that kind of interacts with the realization of that in the true product?
Yeah, that's a great question. So the part where that stuff is like the most useful is in like the earliest days of like developing the vehicle. And like if you're constantly just changing what your vehicle is looking like that's where it's like really important to have the most, easy to use, like like iterate on tool, which I think Julia is a little better for. When you're a little bit like your vehicle's a little more mature, you start to lean more on like the software style of thing. With that said, we're still doing a lot of active development work and controls development work, and we always will be. And it is, yeah, like that is a huge thing missing in the Rust community. What we do is we'll still use Julia, or some people are using MATLAB. It's kind of like, grab bag for different teams and stuff like that, or Python for doing like a very specific analysis, but like that analysis won't be necessarily something that plugs into our main sim. Like if you're doing a linear controls analysis, you're kind of like building up your linearized thing from there. If you're not like linearizing it in the model, which we had in Julia, which is kind of sad to leave behind. But yeah, there is a lot you're giving up on that side. And that was like very clearly going into this, one of the trade-offs we were going to have to make. But just given that we have so much of the company that like relies on this infrastructure that, needs to land on Julia, that it ended up being the right trade, I think, there. So it's a little bit harder for a small group of us like me. Cool.
So I might be a few years out of date asking this, but when I last checked and this was a blocker for me using Rust, a lot of the numerical stuff that like ages ago was in Fortran and people have written in C. I'm thinking about ODE solving. I'm thinking about like finite element stuff. It didn't exist at all in Rust, at least a few years ago, and like in really and there were some like packages that were kind of kludging on the Fortran stuff, and so you lost all of the benefits of Rust. Is that still the case, or is that does that ecosystem, like you had it on your slide, no SciML ecosystem? Is that better now, or is it something you're doing in house, or
It's
you
a
don't
little
need
bit. Yeah, we're doing it in house, our ODE solving. Just mostly because we don't have that. We do have a lot of requirements. We do have like a finite element tether, but like we're kind of doing stuff to work around that. But yeah, there are a couple ODE solving like packages in Rust, but they're very bare bones, like give it a vector, and there's not like a lot of like, callback, or there's like a output grabbing callback and stuff like that. But it's not to the point where you were saying where it's like calling into Fortran. At least like most of them are written in pure Rust, so it's nice for that. But you're not gonna get like hundreds of different solvers and have a whole callback ecosystem and all that kind of stuff.
I'm just curious what the plans for Starling and modeling.jl and so on are in terms of will they be open sourced, or are there sort of an open?
Yeah, that's a great question. Certainly we couldn't do Starling because that has like a lot of our specific flight stuff, but modeling.jl purposely was kept aside in the intention that maybe one day we would open source it. And I think a lot of people are amenable to that. I don't think we would want to invest any time in maintaining it, but like possibly I could just get it under my own name and do that, and I wouldn't mind doing that at all. So yeah, that's a great question. I don't know.
So let's thank Jonnie